And we're on the air yet again. Here we go. Let's get started. All right, we're in section 1.1 of the textbook. So let's take a look at some questions that relate to that stuff. All right, so we're chapter 1 is linear functions. What's a linear function? Anybody know? What? Yes, you can graph it. What else? Anything else? Linear. What does that sound like? Line. All right, when you graph it, it's a line. Okay. So let's see some examples of that kind of stuff. Let's see. All right. Let's say I gave you the following data. All righty? So, well, it's fast again. All right, let's make it, is this a different color? Let's make it red. All right, so let's say I give you, let me think of this. R, wow, this is very sensitive. R, the chirp rate, and T, the temperature of a cricket. Now, I don't know if you know about this, but depending on the temperature, crickets will chirp faster or slower. Okay, so here's some data. Let's see, can I get, is there any, like, geometry here, like lines? No. All right, forget it. All right, so I'm going to give you a little table. Wow. You know, I don't like this. This is not a good pen app. Okay. Zing. Give me a pen. Zing. Okay. So here's some data. The chirp rate is 20 chirps per minute. It's going to be some real data. When the temperature is 45 degrees Fahrenheit. All right, so I got to say that R, the units of R, is chirps per minute. Yeah, go away. Okay, and the units of T, what is that? You know, this app really is bad. Okay, the units of T are degrees Fahrenheit. Sorry, my handwriting is terrible on here because it doesn't work too good. All right, so at 45 degrees Fahrenheit, you have 20 chirps per minute, or 20 chirps per minute means it's 45 degrees out. So it's a way to predict the temperature. You don't need a thermometer. You go outside, you listen to the chirp rate of the crickets, and you know what the temperature is. Okay? All right, you get a chirp rate of 40 chirps per minute at 50 degrees. You get a chirp rate of 60 chirps per minute at 55 degrees. And 80 chirps per minute at 60 degrees. And 100 chirps per minute at 65 degrees. I got more data here, but that's probably good enough. My question to you is that a linear function? First of all, what's a function? Anybody know? What makes something a function? If it passes the vertical line test, have you heard of that when you graph it? What that means is that for every input, usually x is the input, y is the output. Here the input is what? R, and the output is t. So think of r as the x-axis, that's all. It's not x, it's r, big deal, right? Think of t as the y-axis, okay? So call it t instead of y, big deal. Is that going to kill anybody? You okay? All right. So what a function is that for every r, there's one and only one t. It's unique. If I have 20 chirps per minute, I know it's 45 degrees. It's not 45 degrees today, 60 degrees tomorrow, 100 degrees today, right? It's always around 45 degrees. This is probably an estimate, but there's a unique y value for every x value. Have you heard of the word domain and range? The words domain and range? What's a domain? What you can plug in to your function, right? What's your range? What you get out, your output, what your y value is usually, right? Okay. Again, it's not always x's and y's. This book doesn't like x's and y's. You'll note there's not a lot of x's and y's, okay? Real world data in science, right? Anyone taking some kind of a technology or science major? That's why you need math usually. Yeah, okay. You're probably going to see this more often than x's and y's, right? All right. So so is it a function? It's for every r there's only one t. How would it look if it was not a function? Inconsistent? More, give me more. I need more. Yes, but more. No? Right. What if the R values were repeated? Like somewhere down, it doesn't have to be in order, by the way, right? I happen to have them in order, increasing R's, but it doesn't have to be, right? Say later on in the list there's another R equals 20, and then T equals, I don't know, 200 or something, right? That's a dead giveaway that for one R, there's two Y's. For one R, there's two T's. That's not a function. If you graphed it, that would not pass the vertical line test. Right? You know about parabolas? What's a parabola? It's like this U shape, right? I call this a smiley face parabola and a frown parabola, right? A smiley face, is that a function? Everywhere you draw a vertical line, it hits the graph in one place. But what if I have this kind of a parabola? A parabola that opens from the origin to the right or to the left. Does it pass the vertical line test everywhere? And in most places it doesn't. Almost everywhere it doesn't, right? So that's the thing. All right, so this is a function. Now, is it a linear function? What makes it linear? What makes it a line? They're all straight. That's redundant. Straight line, thank you. I know, it's straight. But what makes it straight, though, that's important. What makes it straight? The average rate of change. What am I saying? What are you saying? Starts with an S usually. The slope is always the same. Is the slope here always the same? Let's see. What's your delta T here? What if I subtract 50 minus 45? What's the increase in temperature? 5. What if I subtract 40 minus 20? What's the increase in chirp rate? 20. So if I say, what is delta T? Ugh, that's bad. What is delta T over delta R? It's 50 minus 45. Stop that. I do not like this pen app. What are you doing? Go away. Minus 45. Why is it doing that? You know why it's doing that? Because I don't have a multi-touch tablet and I'm touching it in two places. That's why. Okay. 45. There you go. Over 40 minus 20. Oh, please excuse my awful handwriting. All right, so what's 50 minus 45 you said already? 5. And what's 40 minus 20? 20. And by the way, can you reduce that to what? 1 quarter? 1 quarter? Okay. And what are the units? The top is temperature and the bottom is chirp rate. So that would be degrees Fahrenheit per chirp per minute or whatever. Okay, degrees Fahrenheit per chirp, let's say. Okay, so if the chirp rate increases for, where is my pen? This is hard not to do with multi-touch. Okay, so for every increase in a chirp rate of 4 chirps, the idea is that the temperature will increase 1 degree Fahrenheit. Right? That's a rate of change. We call that an average rate of change. But is it the same everywhere? If it's the same everywhere, it's a line. If it's not the same everywhere, it's some kind of a curve. All right, so we already figured out it's a function, but we don't know if it's a line. So let's do it again. What's your delta T here? By the way, do you know this word delta? What am I saying? Change, right? Delta is just, I guess they do this in chemistry a lot, right? Delta means change. Delta T, change in temperature. So I'm just subtracting temperatures. Right? Have you never calculated slope given 2 points? M equals y2 minus y1 over x2 minus x1. Didn't they make you memorize that craziness in high school, right? No. Just subtract your outputs, subtract your inputs in the same order. The thing with the y2 minus y1 over x2 minus x1 is make sure you do this in the right order, because is subtraction commutative? Is subtraction commutative? No. What does that mean? That 50 minus 45 is 5. But 45 minus 50 is not 5, right? So the order of subtraction matters because it changes the answer, right? So now notice I have a positive slope. What does that mean? It's going upwards. When you graph it from left to right, I have to do right to left for you guys. From left to right, this is my right, but that's your left. Okay, so from left to right, the function's going up. Now, but is it going up linearly? Well, let's see. Is your delta T over your delta R the same? What's your delta T now? 55 minus 50 is 5. And 60 minus 40? 20. 60 minus 55? 5. 80 minus 60? 20. It doesn't always have to be 5 over 20, but it always has to reduce to 1/4. Okay, good. So this is an example of a linear function. All right. So let's say I'm running around. Let's see. How would I? Okay. Can I graph that? Now the thing is, we're supposed to be using the graphing calculator, right? Oh boy, I don't have a graphing calculator. Hang on. See, there's more. Okay. Note to self. Install USB mic. Install USB Bluetooth transceiver. Run screencast-o-matic.com. What else? What else did I do? Use, what is this? Windows Journal as a pen app. I don't like it, but we'll see about that. And get yourself a calculator. There's no USB ports up here. I have a virtual calculator. It looks like it's the 83. Okay. No, you're in a dangerous location. Don't mind me, YouTube. Hang on. Let's see. This is going to fit. All right. Like I told you, I've been using graphing calculators since like forever. That's why I have reading glasses, I think. The calculator's messed up my eyes. You see the screen? It's low res. Okay. It's low res. It's not backlit. It's grayscale, right? Ugh. Sorry, you guys can ruin your eyes. I'm not doing that. So let me see if I can find my drive. I have a calculator in here somewhere. Hang on. Computer. All right, where is it? I know it's in here. Hang on. All right, so there's 5 components. A pen app, the tablet, the mic, the screencast-o-matic, and now the calculator. So where are you? Oh, here it is. T83. Go. Ta-da. Yeah, you thought I was foiled again. You thought wrong. Okay. So how are we going to graph this crazy thing? Can we graph this? And now, some of you said you were taking statistics, or were going to take statistics, or took statistics. You ever do a scatter plot? Right? You know what a scatter plot is? What is that? It's just the dots, right? All right, let's just graph the dots, right? Do you know how to do statistics mode on here? Do you know how that works? No? All right, go to, make sure it's on. Okay. All right, then you go to second y equals a stat plot. All right. Now this is a T83, but it's similar in the 84. If you have an 84, that's fine. Okay. You should have a graphing calculator following along. If you don't have one, get one. You can mug your younger brother or somebody. All right. So so hit enter, and let's turn it on. Now here it is. It defaults to a scatter plot, just the dots. I'm going to put data in list 1 and list 2. You can pick your favorite mark. Every dot will be marked with a square or a plus sign, or a dot, right? If you hit enter, it'll be a dot. If you go over here, you use your Nintendo keys to navigate, right? Nintendo keys there. You hit enter, right? I'm going to stick with the squares. Now L1, L2, where's that? Well, second mode is quit. How do I enter the data? I want to enter this. So you go to, anybody know? Stat, edit, there you go. Now if you got junk in there, right, if you've used this before, you can go to the top of the list, hit clear, enter, and go to the top of the list, clear, enter. But I'm blank. I don't know if you're blank. Are you blank? Okay. All right, so let's enter the stuff. All right, so now list 1 in the stat plot is the x values, and list 2 in the stat plot is the y values. But for us, list 1 is R, and list 2 is T, right? So list 1, 20, enter. 40, enter. 60, enter. 80, enter. 100, enter. Now I got more data, but that's good enough. All right, and then 45, enter. 50, enter. 55, enter. 60, enter. 65. All right, so how do you make it plot the dots? There's a way to make this figure out your X-min, X-max, Y-min, Y-max to fit all the data. Do you know how it goes? No? You never used this before, this mode in the calculator?
I think you go to graph, right?
You can go to graph, but it may not have the good window. I would go first to zoom. Do you know? Zoom 9. Now, I usually set my window size the way I want, whatever X-min, X-max I want. But this is nice. Zoom stat will make the window big enough to include all the dots. Now, so does it look like if you connected the dots, you would get a line? So it is linear, right? Guys, I know I said this is not for the faint of heart. We're covering 3 chapters this week, right? But it's just lines today, okay? It's not, don't get crazy. You're getting crazy. It's just lines, okay? What? Did you get this? Zoom 9, zoom 9. So follow along with your calculator so you know how to use your calculator on my test. Okay. Now, how do I make it come up with the equation of the line? Do you know how to do a regression? Linear regression? No? Have you done this? Sounds like you've done this, right? You've done this? All right, let's do it. Linear regression. So I'm going to quit. Second mode is quit. Go to Stat, Calc. Stat is here. Then right arrow key is Calc. And linear regression, number 4. Now, if I hit Enter, it tells me the equation of the line. Now, are you familiar with the equation of the line being y equals mx plus b?
Yeah.
Right? Notice what it said here. Y equals ax plus b. So what's a mean? A is the slope. Instead of m being the slope, a is the slope. Is that okay? It's just calling it a. So it's the same thing, okay? Now, didn't we say the slope was 1/4? What's it saying? A is what? 0.25. Is that a quarter? Amazing. Magic. Phenomenal cosmic powers. Itty bitty little circle. So, you guys know that movie? Aladdin? Yeah. Yeah, there you go. Now, how do you make it graph that for you? Can you make it graph that? Like if I go into y equals, it's not there. Do you know how to make it graph that? This is what you do. Stat, calc, 4. Now, if you wanted to actually write out the equation for you and copy it into y1 so it'll graph it automatically, you have to write the list that you're using. What did we use? List 1, list 2, right? So go to second 1 for list 1, comma, second 2 for list 2, comma, and then where do you want it typed in? It'll type it in for you. Talk about lazy. You don't have to type nothing. You just do clicking. It's okay with the mouse. If you have a virtual calculator, it's a mouse. You got to use your fingers. Okay. So what do I want it? I want it in y1. Do you know how to get y1? Do you see the vars key? Are you following with me? Vars key. Vars. Go to the right. Y vars. Go to 1 function. Hit enter. Hit 1, and y1. What does that do? When you hit enter, you get the same stuff. But when you go to y equals, it's there. You didn't have to type it. And when you go to graph, it graphs the line. And it looks like a pretty good match. All right, the correlation coefficient should be about 100%. Guys ever hear of correlation coefficient? Coefficient of determination? Statistics? No? How do I get that? Well, notice what it did. It only gave me A and B, which is fine. That's what I wanted. But I also wanted to know how good a match this was, how linear this really is. There's a way to figure that out. There's this thing called R squared, which is the correlation coefficient. And if R squared is near 100%, you got a good match. If it's positive, you have a positive slope. If it's negative, you have a negative slope. If you have anywhere near 100%, it's a good match. How do I get that? Well, you have to set that. Go to mode. No, sorry. Go to catalog. Second, 0. Okay, now I need something called diagnostics. Now you can down arrow all the way until the D's if you want, but I'm going to just hit, see the green D? See the green up here is the green D? Hit that because it's in alpha mode. Jumps down to the D's. And go to where it says diagnostics on, I think it is. Diagnostic on. Hit enter, hit enter. Now, if you run the previous command, how do you run the previous command without retyping everything? Do you know? You guys got to get used to this calculator, I'm telling you. Second, enter. I don't want that. Second, enter. Oh, that's what I want. Enter. What's different here? It gives you this thing called r squared, the coefficient. I think that's the coefficient of determination, and r is the, what the heck did I just say? Correlation coefficient, right. Now, r is harder. R squared is harder to get to 100%. I usually look at r squared, but r is the correlation coefficient, and r squared is the coefficient of determination. I mean, think of it. What if r is only 60%, 0.6? What if you square it? What do you get? What's 0.6 squared? What's 6 squared? 36. So 0.6 squared is 0.36. So r squared is going to have a harder time getting close to 100%. This is 100%. What does 100% mean? 100%. 100 divided by 100%, per 100. 100 divided by 100 is 1. So that's what that is. That's 100%. Okay? If you don't like that, you can set your mode and make it round off to whatever, 3 places or something, and then run it again, and it'll round it off to 3 places. But notice there's no error. It's 100%. Okay? So, we've got the equation of the line, don't we? Y equals 0.25, or 1/4, of x plus 40. But remember, for us, x was the r, and for us, y was the t. All right, so let's go to a new page. Let's write that down. So I got that y equals 1/4 of x plus, what was it? 40. Okay, but that's the calculator, because the calculator is stuck using x and y. But for us, the y was the temperature, T, and x was the trip rate, R. I could even write it this way if I want, 0.25 R plus 40. All right? So that's the result. So there is like y equals mx plus b, but it's not y all the time, it's not x all the time. Who's stuck? Anyone like lost? We're talking about what's a function, we're talking about what's a linear function, we're talking about what's a line, what does the equation of a line look like, what does the graph of a line look like. That's all we're talking about. Okay, are we okay with this so far? Okay. Think about this. Okay, good. All right, so let's say I want to extrapolate. What? What the heck does that mean? What if I want to extrapolate? What does that mean? If I get a data point off this chart, like say 100, like 200, say. Do you know what the temperature is for a chirp rate of 200? No. That's called extrapolating, taking the data farther than what we got. Our domain right now is 20 to 100. Our range right now is 45 to 65. 45 to 65. But what if I go beyond that domain? That's called extrapolating. What if I fill in the gaps? What if I want to know what happens at a chirp rate of 50? Do I know? Is 50 in there under R? That's called interpolating. Now, they make a big deal about this in statistics class. It's sounding like a statistics class. Don't worry. I don't teach statistics. Don't worry about that. But they make a big deal about this, that for the domain that you're given, you're usually okay with assuming that if it's a line on your graph, it's a line everywhere on that domain. But something weird might happen beyond that domain. So at r equals 200, it may not be a line. So they say that extrapolating may not be accurate. Interpolating is usually pretty accurate, but extrapolating is not. So how would I extrapolate r equals 200? How would I get the temperature at r equals 200? Any ideas? What? Just sub it into the equation we got. Right, exactly. All right, so what if I say, give me a pen. What if I want to say, what's the t value at 200? I'm using function notation, like f of x. Are you familiar with that? So t of 200 means plug 200 into the independent variable r or x, okay? So I want a quarter of 200 plus 40. Well, can you do that in your head? What's a quarter? Do you really need a calculator for this? What's a quarter of 200? 50. And plus 40 gives 90. So if the chirp rate is 200 trips per minute, your assumption is that it's 90 degrees Fahrenheit outside. That's an extrapolation. So we can use the rule, we can use the algebraic rule for the equation of the line, y equals mx plus b, to predict behavior, future behavior. What about interpolating? What's t of 50? Let's see. Hello, where's my pen? What's t of 50? That means plug in 50 where you see r and figure out t. So what's a quarter of 50 plus the 40? Now this is order of operations stuff, arithmetic. You know your please excuse my dear and Sally stuff, right? Do you add first or you multiply first? Multiply first. So a quarter of 50 or 0.25 times 50 is 12.5. A quarter is a half and a half, right? So a half of 50 is 25, a half of 25 is 12.5, yeah. Plus the 40 gives 62.5, right? Then we say 12, no, 52.5. So that's my interpolation at 50 chirps per minute. I'll assume that the temperature is 52.5 degrees. No, you're rounding off the nearest whole number. Be careful on your calculator. I usually tell it, I go to mode, I usually tell it to round off to 3 places. What you have, you probably have it rounding off to this, 0 places. So it rounds off to the nearest integer. So if you say, what was it now, 50 divided by 4, you're going to get rounded off to 13, but that's not correct. It rounds off for you. So if we do mode, float means it'll put the decimal wherever it wants. It floats the decimal. This is fix 3. If I fix it to 3, it gives you 3 decimal places no matter what. So now if I do that, second quit, second enter, enter, it's really 12.5. And the zeros don't matter, really. Okay? All right, so you can use a calculator if you want to do it. Okay? If you want to use a calculator for arithmetic, whatever, that's fine. Notice what we're doing in this book. We're attacking the problem 4 different ways. Okay? We're looking at the data or the situation or the phenomenon, whatever it is. We're looking at it graphically. We're looking at it numerically, like that table of values, like the graph that we had, right? Analytically or algebraically, we're writing in the formula, an equation, right? And, yeah, I don't like this. People say verbally. But that's not catchy. GNAV, that's not catchy. So I do this, wordily. I gnaw at my problems. Every problem I come up with, if I don't know what to do with it, I just play with it. I start gnawing at it. I look at it graphically. If that doesn't help, I look at it numerically. If that doesn't help, I look at it algebraically. Somewhere along the line, I'm going to get some kind of an answer, some kind of a pattern, some kind of a feel for what's going on, and then I can explain wordily what's going on. Okay? So that's really the kinds of questions you're going to see on the homework. Many of them are word problems. They give you a situation like we just had, the chirp rate. They ask you to look at it graphically or numerically or algebraically and ask you questions about it. And then part of the answer is verbalizing. Why do we hire English teachers? You want to tell me? So you can write your answers in English on a math test. Didn't you know that? That's why we hire English teachers. That's the only reason. So I like to gnaw at my problems, right? So I look at things graphically, numerically, analytically, or algebraically, and then I verbalize my results. My answer I write in a sentence form. Okay? Like this answer. How would you verbalize this answer? This answer right here. When you plug in 200, you got 90. Give me a sentence. Verbalize that. Write that in English. If the chirp rate is 200 chirps per minute, then the temperature outside is around 90 degrees Fahrenheit. Right? That's it. Now, what that forces you to do is throw in units. So if there's units in the question, there's units in the answer. When you verbalize it, it doesn't make sense to say the chirp rate is 200 and the temperature is 90. 90 what? Kelvin? I don't know. Celsius? Centigrade? What? Doesn't make sense. When you verbalize, if there are units in the question, there's got to be units in the answer. Okay? You should verbalize your final answer every time you're done with a word problem. Okay. So there you go. Let's see. Is there any way to tell how long I've been recording? No. All right. I could. Is it recording? Oh, geez. I don't think I recorded. After all of that, did it start recording? What is this? Oh, yeah. Oh, boy. Are you recording? It's not recording after all of this. It's not recording! Damn you. Didn't I start the recording? Oh, it says pause recorder. So it is recording. It is recording. Okay. Usually when it's recording, it has a little thingy on the bottom here. It can stop it, pause it, whatever. All right. Hopefully it's recording. I don't know. What's this? Is this it? What's this? No? That's weird. Usually there's a little thingy down here that says I'm recording or I can pause it or whatever. I can't. I'm not going to worry about it. Okay, so there you go. So that's what a linear function is. All right. All right, so that's section 1.1. Let's not spend forever on section 1.1 because I want to get to more stuff. All right, so section 1.2. Rate of change. Well, actually, we're sort of ahead of ourselves because we already talked about the rate of change. That delta t, what was it, delta t over delta r, the slope, that's the rate of change. They call it the average rate of change. When you get into calculus, you're going to talk about the instantaneous rate of change. They're related, but they're different. You ever hear of the concept of limit? Ever do a limit? No. Scratch that. I didn't say nothing. Top secret. If I told you I'd have to shoot you, top secret. No. That's next semester. All righty. So let's see. Let's come up with something else. Let's see. All right. Well, not everything is linear. Let me give you some more data. You ever hear of carbon-14 dating? You know how they do that? What's that for? What do you do? Yeah, to date old stuff, maybe fossils. There was a famous case a few years ago. You ever hear the Shroud of Turin? No? The Shroud of Turin, it's called of Turin because it was found in a monastery in Turin, in a basement, underwater, falling apart in pieces. The monastery burnt down in the 1700s or something. They were excavating this, archaeologists, they do this, they got nothing better to do. And they found this thing, and the shroud means it's a burial cloth. And supposedly this is the burial cloth of Jesus. Okay? It says so, marked. Burial cloth of Jesus. So they're like, what, really, huh? So they sent, the Vatican said, I need to see this, bring this here. Okay, so the Pope is looking at this, he's like, maybe. So they commissioned a bunch of scientists to do the carbon-14 dating. And so how old, now I'll give you a hint, this was found in 1988. So if you carbon date the Shroud of Turin, how old should it be? 1,988 years old, because that's basically, we're measuring the time since his death, right? Okay. But they did the carbon-14 dating, and they figured out there was only 800 years old. So it's a fraud, right? It's not the Shroud of Turin. It's not Jesus' burial cloth. Maybe. Because there's a lot of error involved. They found it in a damp, musty basement. It was there for hundreds of years. It was wet. It was falling apart. It was in the monastery after it burnt down. There might be some extra carbon thrown in there when they burned down the monastery. So it's still in debate. But here's an example of carbon-14 dating, okay? So carbon-14, by the way, why does carbon-14 dating work on a burial cloth? How do you date that? Look, carbon-14 is a radioactive element that exists naturally in the atmosphere. It's absorbed by living organisms. That's a hint. So how does carbon-14 dating work? You have to figure out how much carbon-14 is there. It's a radioactive isotope, so it decays over time. Okay? You got to figure out how much carbon-14 is present in the object right now, right? And then you have to make, archaeologists do this all the time, an estimate of how much carbon-14 was present in the I don't know, atmosphere at the time, right? But the Shroud of Turin, it's a cloth. It's not alive. How does this work? How does it ingest carbon-14 from the environment? Aha. Because it was made out of lamb's wool or sheep wool or something, right? So what does that mean? Well, the sheep was alive, walking around eating carbon-14 all over the place. It got into its wool, its hair, and so when you kill the sheep and get the skin off it, and I don't want to go there, okay? The thing dies, it doesn't bring in any more carbon-14, so whatever was there, you can figure out how much of it has decayed, and you can figure out how long that took, right? So that's how carbon-14 dating works. So here's an example of carbon-14 dating. So carbon-14 is a radioactive element that exists naturally in the atmosphere and is absorbed by living organisms because we eat organic materials that are based on carbon, right? Do you eat organic materials? Food is organic, right? What does organic mean? It's got carbon in it. Okay. When an organism dies, the carbon-14 present at death begins to decay radioactively. Let L equal G of T represent the quantity of carbon-14 in micrograms in a tree T years after its death. And here's a table. Okay, so here's another table. So we're looking at this numerically, right? Okay, so let me get a new page. I hope this is recording. I hate this. Okay, give me a page. Okay. So here's some more data, okay? I wish there was a way to make tables in here. Insert. Picture, no. Action, tools, pen. You would think there would be a way to do like a chart or something. Nah. All right, whatever. So I'll just draw it. So here we go. So let's make a table. Trying to make it neat. Sorry, can't do that. So let's say your input is T, how many years the carbon has been decayed, and L, the quantity. I don't know why they called it L, but okay. L, the quantity in micrograms. All right, so the units of T are years since death of the tree. Okay? And L, the units in L are micrograms of carbon-14. Okay? All right. So let's say initially T equals 0. Come on, give me a pen. T equals 0. We start off with 200 micrograms of carbon-14. Okay. 1,000 years later, we only have 177 grams because it's decaying. Wow. Sorry, this tablet's getting stuck, so it's not writing what I want. All right, after 2,000 years, that's a 177, okay? I have 157. Let me fix that. This is a mess. Okay, whatever. After 3,000 years, so if you're dating something that's supposedly 3,000 years old, you would expect to see 139 grams of carbon-14 left in the organism. That's not a 3. Wow. My kingdom for a real smart board. And 4,000 years, it decays to 123. And in 5,000 years, it decays to 109. So question number 1, is this a function? As far as you know, just given this amount of data, yes, right? There's no t value that's repeated, in other words, right? You can have a repeated y value, L value, but not a repeated t value. So let's say the domain, the x-axis is t, the range, the y-axis is L, right? Okay. Is it linear? What's your average rate of change? What's your slope? Is it always the same? Let's find out. What's your delta L from here to here? What is that? This, here to here. What's your delta L? 200 minus 177 is? How much? 23, okay. And 0 minus 1,000 is? Negative 1,000, right? Okay, so let's write that down. Your delta L, instead of a delta y over delta x, like slope, m slope, right? Instead of delta y over delta x, it's delta L over delta t. Subtract some L values, 200 minus 177. That's what delta means, change. What's the change? Right? Subtract, find out the change in the value. And in the same order, if I start with 200 for L, I got to start with 0 for t. Because the order matters. If the slope is negative, that means it's decreasing. If the slope is positive, it means it's increasing. If you don't do that in the right order, you're going to get the wrong sign, right? All right, so you're saying it's 23 over 1,000, and it's negative, right? Okay, so 23 over negative 1,000 makes the whole thing negative. Now, when you write a fraction, I don't care where you put the negative. You put the negative on top with the 23, or the bottom with the 1,000, or in front. It's negative, okay? It means the same thing. All right, so that's not a fast rate of change, but what does that mean? Is it increasing or decreasing? Decreasing. But is it linear? How do you know? Do it again. The delta L over delta T must always be the same for it to be a line, for it to be straight, okay? So let's do it again. How about somewhere else? Let's say from delta L from here to here. What's 157 minus 139? That's a 3. Wow. This tablet's not cooperating today, sorry. Or the mouse or something. The mouse settings. So what's 157 minus 139? If you have to use a graphing calculator, go for it. 18, right? And it's still a negative 1,000 on the bottom here, right? Because 2,000 minus 3,000 is still negative 1,000. So 2,000 minus 3,000. What'd you say, 18 on top? All right, so it's 18 over negative 1,000. How about negative 18 thousandths? So is the slope always the same? What I'm calling the average rate of change. It's not. It's not linear. All right, let's see why not. Let's graph this thing like we did before. Let's go to the calculator. Let's change our stat edit. And let's enter this data. Now, I could just type over it, I guess, or I could delete it. Let's delete it. Up arrow, clear, enter. Left, up, clear, enter. Let's start from scratch. Okay. All right, so enter it in. 0, enter. 1,000, enter. 2,000. If you know sequences in series, there's an easy way to do this, but this is not a course in sequence in series yet. 4,000. Actually, that's the last chapter. 5,000. One of the last chapters. All right, did I enter that right? I think so. So that's 6 entries, right? Okay, good. Then it's 200. And it's 177. And it's 157. You'll see that it's not linear when you graph this, the scatter plot. Okay. Now, is my stat edit correct? Yes, stat plot 1 is on. If you look at it, it's a scatter plot using list 1, list 2. Okay, that's great. Let's do a zoom 9. It's probably different X-min, X-max. And whoops, what's that? What is that? That's not supposed to be there. What is it? That's the answer from the previous question. Go to y equals, clear, graph. All right, there it is. Now, does that look linear? Possibly. It's hard to tell, isn't it? If you magnify any curve sufficiently much, you blow it up, you blow it up, you blow it up. You make the distance between X-min and X-max smaller and smaller and smaller. And we're blowing it up on the screen. It's like magnifying it, stretching it out. Any continuous curve will eventually look linear. So it's hard to tell. But let's try it. Let's see. Can we try and get a linear regression? How do you do that again? Let's do it again. How do you do that? Yes. Stat. Calc. 4. 4 and 8 basically are the same, by the way. But it writes it backwards. Some people like it that way. A plus bx, where b is the slope. You can use 8 if you want. I like 4. Enter. Now, you could do this and get an answer. But I want to graph it too to see how it fits the data, right? How do I make a graph? Look, it's not here. What did I forget on purpose? What did I forget? How do I make it write all of this stuff here so it automatically graphs it when I hit graph? You forgot? You do this, but you also do L1. Second 1 is L1, comma. Second 2 is L2, comma. Vars, y vars, function 1, or whichever one you like. And it does the same thing, but now it's here, so I can graph it. It's not really hitting all the points nice like last time. It's close. It's almost linear. Look at this. What's the correlation? The coefficient of determination is not 100%. It's close. For this domain, it's almost linear. But if you had more data, it probably wouldn't be. So I want to try and get more than 100%. How do I make it more than 99.2%? How do I make it better? It's not a line. What shape is that? Do you have any intuition on what shape that is? It's decreasing, but it's got concavity. You know concavity? It's concave up a little bit. I'm exaggerating. It's concave up. What, do you know about concavity? Concave down, concave up. The slope is increasing. It's concave up. Slope is decreasing. It's concave down. Well, notice this is, I'm thinking this is concave up in that the slope is increasing. Why? Because the slope is negative. So to increase it, it's trying to get more and more positive. If it's negative, it's trying to get closer and closer to zero is what it's doing, right? So that's not a good estimate. So go back to quit this. Second mode is quit, is the home screen, right? How about we do stat something else, stat calc something else? How about quadratic? What does that mean? That's a parabola, right? It gives, all right, let's see how good a parabola does. Second L1, comma, second L2. And remember, we had 99.2%. Let's see if we can get better. Comma, vars, y vars, function 1, enter. Now, now for this one, it doesn't give you r, but r squared is 100%. So it's quadratic. Look at that. For this domain, it's quadratic. Look, it's hitting, no, it's not. What happened? Wait, something's weird here. It's not quadratic. Look what it's doing. It's putting a 0 in front of the x squared. So this is not a good model because it's giving me a line again. It's doing mx plus b again. Look, it's 0x squared. There's no x squared here. That's bad. That means it's not a quadratic model, even though it's saying 100% correlation of the coefficient of determinations is the r squared. Yeah, that's bad. Do you see that a isn't 0, but it's damn close? What does e to the negative 6 mean? It says that a, the first coefficient, it's in scientific notation. It's 1.089 times 10 to the negative 6. Means move the decimal 6 places to the right. 6 places to the left, making it smaller. So it'll be point. It's point what? How many zeros? 5 zeros. Then it's 1 etc. So it's very small. So when it was writing it here, it to 3 places. Remember I told it to round off to 3 places? It's basically 0. If I change the mode and I put it to float, let's see what happens now. Now you got a zillion decimals. What happens here? This is a mess. But look, it's not 0, but it's damn close to 0. 0.0000018, right? It's damn close to 0. So this is really not a parabola. That's not a good choice. Even though the correlation coefficient said it was good. It's not even 100, see? It's better, but it's not 100. All right, I'm thinking it's exponential. Now, this is something I'm not expecting you to have an intuition about yet. But this course is about functions, different kinds of functions. Linear functions, quadratic functions, power functions, logarithmic functions, exponential functions, trigonometric functions. Eventually, you're going to have a hang for what the shape is, and you would say that a better match would be stat calc, I think exponential decay. This one. That's how this one works. So second L1, comma, second L2, comma, let's replace vars, y vars, function 1. And now the r squared is damn close to 100%, and the coefficients are none of them 0. So when you go to y equals, there it is, but that's a mess. I like to do this just to make it clean. Second quit, second enter. Make it easier to write. All right, so when you have say you're doing your homework or you're doing a test or something, and you want to write down an answer, and it's got wacky decimals. Decimals that go on and on and on and on. You can just round off to 3 places for me. That's fine. Okay? So this is good for an answer on your homework or on a test or something like that. And if you go to y equals, that's a lot easier to type, to copy down on your paper. Okay? It's saying that b is 1, really? Okay. Let's see how that graphs. Whoa. What happened? What happened is it's graphing this. But that's not right. See, what's wrong with this? A was 199.987 something, but B was not 1. B was not 1, was it? Look, let's do it again. Put the mode back to float. I guess we better stay in float. I have round off error if I do this. It's really that B is not 1. So when you graph it, There you go. It matches the curve, it matches the points almost exactly. All right? So you know what? I take that back. Don't let the calculator round off for you. You round off in your head if you need to round off. All right? So when you write down an answer like this, you can easily round this off in your head, can't you? 199 point, give me 3 places. Point what? 987, right? If this is 5 or more, round up, right? Point 999, nah. All right, you know what? I take that back. That's inaccurate. Instead of rounding off, truncate. What's that? Just chop off the rest, okay? Because look what happens. If you round this B off to 3 places, the 8 is 5 or more, so the 9 goes up 1, the 9 goes up 1, the 9. You get 1. That's way off. So it's better, I would rather you truncate, okay? So type 199.986, just chop off the rest. That's what truncate means. And 0.999, chop off the rest. Okay, that's more accurate in this case, because look how nice that graphs. That's a lot nicer. Okay? All right, so there you go. So it's not linear. And how do we know? Because your delta L over delta T was not always the same. Okay? So now you know if it's a function or not. Now you know if it's linear or not. When is it linear? When the delta y over delta x is the same everywhere, right? Okay. All right, so that's what section 1.2 is about. It's delta y over delta x stuff, but we started talking about that from the get-go, so you're ahead of the game. You're so smart. It's amazing. All right, what's going on in 1.3? 1.3 is how the heck do you get the equation of the line without scatter plots, without stat edit, without stat calc? Can you get the equation of the line yourself? How do you do that? Do you know how to do that? The y equals mx plus b stuff? By hand? Without a calculator? Ooh, scary. All right, let's try another example. Let's see. All right, here's another example. I'm in section 1.3, linear functions. How do you write the equation of the line? All right, so here we go. A town of 30,000 people grows by 2,000 people every year. Okay. Since the population P is growing at a constant rate of 2,000 people per year, this must be a linear function, right? They're telling you it increases, the population increases 2,000 people every year. What is that? 2,000 people per year. What is that? That's the rate of change, the average rate of change, or the slope, right? So how do you write this equation? Okay, let's see. Let me give you some data. They give you some data here. All right, so some more data. Well, are you happy? More data. Here we go. Give me a pen. Ah, that's how it works. Ooh, sneaky. Okay. So, yeah, please excuse the crudity of my model. Ugh. All right, so let's say T is in years and P is in people. Peeps, okay? So at year 0, we have 30,000 peeps. At year 5, we have 40,000 peeps. At year 10, we have 50,000 peeps. Does that make sense? Didn't we say the slope was 2,000? What does that mean? 2,000 watts, units, people per year. So every year we get 2,000 more people. But notice what they're giving you. They're giving you every 5 years. So if the rate of change is always the same, if this is really a line, if the rate of change is 2,000 people per year, what is it for 5 years? 10,000. And isn't that what's happening, right? So they didn't have to tell you the slope, did they? Okay, so we could calculate this all from scratch. So guess what 15 is going to be? 60,000. All right, so 15 is 60,000. And 20? 70,000. Oh, say they didn't tell you anything about the slope. What if we graph this by hand? Let's do that. Can you graph this by hand? Okay, what's your domain? 0 to, that's supposed to be a 20. Okay. All right, so let's do a graph. Wow, this is not a good pen app. It doesn't do geometry well. You should just make that straight. Ugh. All right, so let's see. 5, 10. It does make that straight. That's weird. 5, 10, 15, 20. Okay. And 0. That counts as 0 for T and 0 for P, but technically that's the letter O for origin, by the way. Label your axes. This is the T-axis. This is the p-axis over here. Give me, move. Move the pen. Okay, here's your p-axis, really. Go away. What is that? What is it? Okay. I don't want to insert anything. All right, so now what's your range? 30,000 to 70,000. All right, so let's say we do 1, 2, 3 is 30,000. 40, 50, 60, 70. Ugh. So say the units on the graph really are in thousands of people, all right? Just to make it easy. All right, so let's graph. At t equals 0, this is not very uniform. Ugh. I'm usually better at this. If that was what I wanted to get rid of. Give me an axis. Give me a tick mark that makes sense. Okay, so we're starting here. And then in 5 years, we're at 40,000. And in 10 years, we're at 50,000. Pretend it's a line. And in 15 years, we're at 60,000. Don't pretend it's a line because it's not a line. Pretend it's a line because my handwriting sucks. Okay? All right, so if you connect the dots, this is not cooperating. If you connect the dots, you should see a line. God. Pretend to hit the dots, okay? Oh, this is really annoying. This is on the line, 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 okay? All right, so how do you get p as a function of t? That's my question. Given that it's linear, that makes it easy. First, you got to figure out the slope, but they told us the slope. But pretend you didn't know. How would you get the slope if you didn't know? Change in p over the change in t. All right, let's do that. So change in p, let's see, where would I put that? Give me a pen. Okay. Change in p over change in t is, okay, you tell me what to write. What should I write? Pick 2 points. Pick 2 y values or 2 p values. I don't care which. First 2. So 30,000 minus 40,000. Good. Over 0 minus 5. Okay. So what do you get? 30 minus 40,000 is negative 10,000. But 0 minus 5 is negative 5. Negative 5. So what's a negative divided by a negative? Positive. And 5 into 10. 5 into 10,000 is 2,000. And give me units. Delta P is in people, or peeps if you like, people, per delta T is in years, right? Okay. Now, the question is this. Is that going to be the same always? Even if you pick 2 different points. I picked the point 0, 30,000, and the point 5, 40,000. If I picked any other 2 points, would I still get 2,000 people per year? Yes, I will. Try it. 70 minus 50 is 20. 20 minus 10 is 10. 20 over 10, 2,000 people. Doesn't matter which 2 points you pick. They don't have to be consecutive even. Okay? So there's your slope. It is a line. It has a slope. Now, how do you write the equation of the line? Let's see. I'll get another page going here. All right, so we got that the slope m is delta p over delta t is 2,000 peeps per year, okay? It's a peeps. Okay? Now I want to get y, I want to write y equals mx plus b stuff because I know it's a line. Except it's not y, what is it in this case? It's p. And it's not x, what is it? It's t. So can you figure out, you know m. What else do you have to figure out? You have to figure out what? I need m and b to uniquely identify a line. I need the slope and a point on the line, in this case the y-intercept. Realize that b is the y-intercept. Do I have that? Look at the graph. Whoops. Look at the graph. What's the y-intercept? It's 30,000. Now, you don't always have that. So there's another way to do this I'm going to show you in 1 second. But if you have the y-intercept and you have the slope, you're done. All right? So you tell me, P equals what? M is 2,000. T plus 30,000. You're going to find as you graph more and more of these, if you compare the equation y equals mx plus b to the graph, the b is where it hits the y-axis, what we call the y-intercept. Okay? Now, could you have figured that out? Yeah. You could have picked a p-value. Let me pick a p-value. 70,000. I'll plug it in. And put in, just a minute, this thing is not lining up. Okay. And then put in your m value, which was what? 2,000. And I don't know if you have the data in front of you, but when we had 70,000 people, it was how many years? It was 20. I don't want to go to the other page, but there you go. So I'm going to plug in t, and that's enough to figure out b, because b is all that's left. I can figure this out algebraically. So what is 20 times 2,000? Go ahead. 20 times 2,000 is 40,000. So I got 70,000 equals 40,000 plus b. So how do you get b alone? Oh, God, it's algebra. All you got to do is subtract the 40,000 and you get 30,000. Magic. Right? We've said that the y-intercept is 30,000. And it works out that b is the y-intercept. There you go. Perfect. All right, so given some data, if you know that it's a function and you know that it's linear, you know the equation. Y equals mx plus b. But here's another way. There's many ways of writing the equation of the line. Have you ever, that's called the slope-intercept form, m and b, slope-intercept. Have you ever done the point-slope form? So that all you need to know is the slope and any point. It doesn't have to be the y-intercept. Any point. You plug that in, you got the equation of the line. Let's try that. Here's the point-slope form. Now remember a minute ago we talked about the slope formula? Didn't we say that m equals, dang it, that's my m, okay? M equals y2 minus y1 over x2 minus x1. And they made you memorize that in the 9th grade, right? For geometry class, wherever they did that stuff, right? What if you cross multiply? Whenever you have one fraction equals another, this is over what? 1. You can cross multiply. 1 times anything is the anything. y2 minus y1. And m times stuff is, well, you could distribute it or you could write it out like this. Okay? That's the point slope form. Okay? All you have to do is figure out the slope, plug it in for m like we did before. That's not new. Okay, plug it in to 2,000, right? And plug in any point you feel like on the table. It doesn't have to be the 0, 30,000. It could have been the 20, 70,000, whatever, right? All right, now, usually it's written this way. Y minus y1 equals m times x minus x1. The understanding being that you leave x as the independent variable and y as the dependent variable. You don't plug in for them. You plug in for m, you plug in for x1, you plug in for y1. All right, so again, let me use some data. Give me some data from the table. Give me some data we didn't use yet. We used 0, 30,000 and 5, 40,000 to get the slope to 2,000 people a year. We used the 20 to 70,000. Give me something else. 50? 50,000 in 10 years, right? Okay. So plug in what you know, all right? So y minus y1. Now what's y1? I'm using the point 10, 50,000. 10 years, 50,000 people. So what's y1? 50,000. Equals m, but we figured out m. What is it? 2,000. Times x minus the x value, or the years. What was it? 10. Now, is that the same equation we had a minute ago? Let's see. We had, where is it? Basically, y equals 2,000x plus 30,000. Is that the same thing? Is it? The understanding here is that y is really p, right? Let's go over here. Y is really p. minus 50,000 equals 2,000 times x is really t minus 10. Is that the same equation we had a minute ago? P equals 2,000t plus 30,000. Is that the same thing? I'm saying it is. How do you know? The simplest form for the equation of a line is always mx plus b. No matter how you get it, if you get y alone, you're always going to get mx plus b if it's a line. So how do you get y alone, or in this case p alone? Can I solve for p, get p alone? Simplify this a little bit. What do you do with the 2,000? Distribute it. All right, let's do that. So p minus 50,000 equals 2,000 t minus what? 20,000? Okay. Now I want to get p alone, just like up here. P is alone, right? How do you get rid of this 50,000? Add it to its like term. So what's 50,000 and negative 20,000 combined? 30,000. So you get p equals 2,000 t plus 30,000. You got the same thing. So they're both equations that mean the exact same thing. Okay? As long as you have a slope and a point, you can graph the line. Right? You can uniquely define a line by any 2 points, that gives you the slope, or a point and the slope gives you the direction. And that's all we got here. Okay? We've got the point t is 10 when p is 50,000, and the slope 2,000 people per year. That simplifies to the same thing. Okay, good. Any questions how we got, algebraically, how we got the equation of the line without using the calculator? All right, if you can do it without a calculator, you're expected to do so and show the work. If you can't do it without a calculator, then you use the calculator and mimic what the calculator does. Graph, copy the graphs, label the graphs, stuff like that. Okay? Does that sound reasonable? All right. Any questions how you get the equation of the line? All right, so you know what if it's a function or not. You know if it's linear or not. You know what the graph looks like. You know what the equation looks like if it's a linear function, right? There's a lot of stuff going on here. We're covering almost all of chapter 1 in one swell swoop. Are you happy? You're not happy yet. You gotta go faster? Okay. No? All right. Let's see, what's good here? All right, here's another example. Let me see if that's a good one. Yeah, that's a good one. Okay. Another way to note whether it's a line or not is just looking at the equation. Notice that t doesn't have any exponent on it. It's not like t squared, right? And p doesn't have any exponent. It's not like p to the 1/2 or the square root of p or something like that. That's a dead giveaway that when you graph it, it's going to be a line. Okay, so when the variables in question, x and y, p and t, whatever it is, right? If there's no exponents, well, if it's not written, what's the exponent if it's not written? T really means t to the first, right? So if everything's to the first power, if all your variables are the first power, the t to the 1, p to the 1, x to the 1, y to the 1, whatever, that's a dead giveaway that it's a straight line. Well, that's redundant, that it's a line. Okay? All right, so there's really 3 forms of an equation of a line that you're responsible for at this point. The slope intercept form, the point slope form, and any equation as long as the variables are both first degree. Okay? All right, so how about this? All right, here's the typical word problem. Question? Problem, comment, anything? Raise your hand if you got something good to say. I want to hear it.
So
No?
the first one was what?
This is called the slope intercept form. This is the y-intercept, right? This is called the point, because you're plugging in like an x and a y. The point slope form. You're still plugging in m. You still got to figure out m, no matter what, right? All right, let's see what's another good example. All right, here's a word problem. They don't give you data. They don't give you a table. They don't give you the equation of the line, nothing. Just words. Well, who's an English major out there? Anyone good at literature? Foreign language, maybe? No? I'm going to be good now. All right, here we go. You have $24 to spend on soda and chips at a party. A 6-pack of soda costs $3. and a bag of chips costs $2. The number of 6-packs we can afford, let's call that Y. And that's a function of the number of bags of chips we decide to buy. Let's call that X. Okay. All right. So here's an example, hopefully that we can model with a linear function. All right. So you have $24 to spend. $24 to spend. Spending moolah. Cash. All right. Yeah, wow, okay. The soda costs $3 per 6-pack. So it's $3 for soda, for each 6-pack of soda. Okay? And chips cost $2 a bag. $2 for chips. Okay? Okay. The question are the number of 6-packs of soda a linear function of the number of bags of chips you buy? Because you only have so much money, right? So all right, let's put it this way. If you bought one 6-pack of soda, you spent already $3. But you have how many bucks? 24. So how much is left? 21. So how many bags of chips can you buy? At $2 a pop. 10. Well, 10.5 technically, but 10 because they're not going to sell you a half a bag, right? All right. Say you bought 2 6-packs. How much money did you spend on soda? $6. How much money's left? 18. So how many bags of chips can you buy? 9. Aren't they related? The question is it a linear relationship? All right. Let's put it this way. If Y is the number of 6-packs of soda I buy, and X is the number of bags of chips I buy, how much money did I spend? Now you just did this. I told you that if I bought 2 6-packs, I spent $6. But in general, if it's Y 6-packs, how much did you spend? Or you were going to say? Let's say Y is the number of 6-packs of soda, and X is the number of bags of chips. It's a word problem. It's wordy. A lot of words. Okay? So if I buy Y 6-packs, how much money did I spend? 3Y. Did you say 3Y? 3Y, right. So that's what you did, right? When it was 1, I spent $3. When it was 2, I spent $6. When it's 3, I'm going to spend $9. Okay, so 3Y. If I buy X bags of chips, how much money did I spend? 2X. What's my total bill? Well, I got $4 to spend today. What if it's $59 tomorrow? What if it's $300 the next day? How much is my total bill? How do I total this up? Plus, right? Add them up. So they add up. They add up to what? How much money do I have? 24. So you tell me, is that a linear function? If you graph that, if you got Y alone and you graphed it, would you get a line? You would, right? Because we just said, if the exponent of Y and the exponent of X are both, what's the exponent of X right now? 1. What's the exponent of Y right now? 1. If they're both 1, it's got to be a line. Why? Because what happens if you try to solve for Y? Can you get Y alone? How would you get Y alone? Subtract the 2X. Okay, so I'm going to write it this way. I'm going to say 3Y equals, I could write 24 minus 2X. I'm going to write negative 2X plus 24. Same thing, just in MX plus B form. But don't forget, you still got to get rid of the 3, so how? It's multiplying, you divide. So Y is negative 2/3 of X plus, well, what's 3 into 24? 8. Right? Isn't it? So your y-intercept is 8. So if you buy 0 chips, you can get 8 6-packs of soda. Does that make sense? So if I plug in 0 for X, I get 8 for Y. If I plug in 2 for X, no. Wait, X is the number of chips, right? Let's make it easy. If I plug in 3 for x, what's y? If I plug in 3 for x, can you find y? What's negative 2/3 of 3? What's 2/3 times 3? 2. I'm saying, what is y? That's all right. Let's go to another page. It's negative 2/3 x plus 8, right? Okay. All right. So if y is in fact negative 2/3 of x plus 8, we are saying that y of 0 is negative 2/3 times 0, which is 0, plus 8 is 8, right? Now, give me a sentence. Verbalize that. What does that mean? I plugged in 0 for x, I got 0 for y. But wordily. Oh, sorry, I wrote that wrong. I didn't get 0 for y. I got what? 8 for y. So verbalize that. If I buy 8 cans of soda, I can only buy 0 bags of chips. Or vice versa. If I bought 0 bags of chips, then I can buy 6 packs of soda, right? Okay. But what if I plug in 3? What's y of 3? Negative 2/3 of 3. I'm plugging in 3 for x, right? The 3's cancel. Plus 8. That's an 8. Equals what? If the 3's cancel, what do you get here? The 3's canceled. There's no 6. What's this? Oh, they're telling me the final answer. That's what I'm asking. I'm asking, what's negative 2/3 times 3? Just that. The 3's, negative 2. The 3's cancel, you get negative 2. Or, negative 2 times 3 over 1, right, is negative 6 over 3, is still negative 2. But you get negative 2 plus 8 is 6. All right, verbalize that. Give me a sentence. If I buy 3 bags of chips, then I can buy 6 packs of soda, right? Okay, so it is linear. It's mx plus b form. It's got to be linear. Yeah. Y is a linear function of x, and x is a linear function of y. I arbitrarily called y the 6 packs of soda. I didn't have to. It would have worked either way. But you make sure you realize which is which, right? If you make y the number of chips, it's going to look different, but the numbers will work out the same. Instead of y's and x's, you can say s's and c's. Yeah, sure, perfect. That's in fact preferable. They like that in this book. Yeah, they do that. Okay, good. All right, so is it so terrible to come up with the equation of a line? Basically, is what we're doing, right? Okay. Alrighty, so, okay. All right, so that's it for today for new stuff. We did sections 1.1, 1.2, 1.3, 1.4. 1.1 is what was a function. 1.2 is what's a linear function. 1.3 was what's the rate of change. 1.4 is what's the equation of a line. We did it graphically, we did it numerically, we did it algebraically, we did it verbally. You guys are off to a good start. Am I getting anybody really, really confused at this point? Who's really, really, really confused at this point? Okay, it'll sink in. You got to get used to using the calculator. You got to get used to when you don't need the calculator. It's your decision. If you can do the work without the calculator, you're expected to show that work and do it algebraically, show all the work on paper. If not, then you got to do a graph or something, whatever you see on your calculator, reproduce it on paper and label the graph and show me what it says, and verbalize your answers, right? Okay, that's the theme of this course: graphical, numerical, analytical, and wordy, verbal, right? Gnaw at your problems. So since that's the end of the new stuff, I'm going to tell this thing to stop recording. Stop recording. Okay, pause recorder. How do you stop it? My screencast.